All right, so we're going to finish up this problem that we started out in the last video. So we already made our lead 2 acetate and our potassium iodide. Okay, those are our reactants. And this is a double replacement reaction. So basically in a double replacement reaction, these guys are going to switch partners. Okay, so the cation of this one is going to go with the anion of this one. The cation of this one is going to go with the anion of this one. Okay, but you do have to look at the charges to see how they go together. All right, so I know that my lead 2 is going to go with my iodine. So lead 2 implies that you have Pb2 plus and iodide ion is -1. Okay, so how many iodines would need to go with the lead 2? We'd need to have 2 of them. And you guys can also do the crossover rule. We'd need 2 of these and we would need 1 of these. Okay, so it would become PbI2. Oops, that was a mistake. I2. That was just supposed to be a 2 there. Okay, good. All right, now we need to put our potassium with our acetate. Okay, so potassium we know has a +1 charge and acetate has a -1 charge. Okay, you're always going to put the cation first, and these guys are already balanced. They're already equal but opposite. So it becomes K and then C2H3O2. All right, so now let's look at it. I have acetate on both sides, okay, and they stay together, so that's good. I have 2 of them on the left side here, and I have 1 of them on the right, so I'm going to have to throw a 2 out in front here to get those acetates to balance, okay, but that gives me 2 potassiums, and I only have 1 potassium here, so I'm going to have to throw a 2 out here to get that to balance. All right, let's look it over and see if we've done it all yet. So I have 1 lead and 1 lead. I have 2 acetates and 2 acetates. Good. 2 potassiums, 2 potassiums, 2 iodines, because this 2 is multiplied across, and 2 iodines. This is iodine here. Okay, so that balances. So this whole entire thing is balanced. Nice job. So we need to learn the terminology for compounds dissolved in water. A compound is soluble in a particular liquid if it dissolves in that liquid, okay? It is insoluble if it does not dissolve in that liquid, okay? An aqueous solution is a homogeneous mixture of a substance with water, okay? So that just means like if I have something that is mixed with water and it disassociates into ions, then it would be aqueous. When an ionic compound dissolves in water, they usually disassociate into their component ions. So if we look at NaCl here, if you were to drop NaCl in water, okay, NaCl in water, it would disassociate into ions and it would be a bunch of Na pluses and Cl minuses. It would disassociate completely in water into its component ions. Now, when you have a solution that disassociates completely in water, so it's soluble in water, okay, that means that it's a strong electrolyte, okay? So electrolytes are solutions that contain ions. Strong electrolytes are good conductors. Ionic compounds that are soluble, and that means that they completely dissolve into ions, are strong electrolytes. So you're also going to learn that strong acids and strong bases are strong electrolytes. So let's go back to this previous picture here. So because you have so many ions in the solution, it would make it very easy for electricity to flow through here, okay? Because the electricity could just flow from ion to ion to ion to ion to ion, okay? So they're good conductors. So as you can see in this picture, You have a battery that's connected to some electrodes there on the left, and you have pure water. Now, if that battery is hooked up to a light bulb, pure water actually it's molecular, and so it does not dissociate into ions in the solution, so you would not expect your light bulb to light up. However, if you were to put some salt in that water, all of a sudden you would have just a ton of ions in there, and now that water would be superconductive, making it a strong electrolyte because the current can readily flow through there and your light bulb would light up. Here's another example of a soluble ionic compound, silver nitrate. Silver nitrate, when it is put in water, you will not have any complete AgNO3 units in there. So only your dissolved ions are present. So again, you would have a bunch of silver plus ions, and you would have a bunch of NO3 minus ions. Those are your nitrates. And this would make this also a strong electrolyte because we wouldn't have any AgNO3s all stuck together just in here, not being able to conduct current. Okay, so this is also, we're going to learn the solubility rules here in a little bit, but this is also something that is considered soluble. Okay, so not all ionic compounds dissolve in water. Okay, so this is why we're going to be looking at the solubility rules here in a little bit. So AgCl is considered to be insoluble. Okay, and so it would remain a solid chunk in water. Maybe like a teeny tiny bit would dissociate into ions, but not enough to really count. So to sum it up, a compound is soluble in a particular liquid if it dissolves in that liquid, and a compound is insoluble if it does not dissolve in a liquid. For ionic compounds, there are some rules. They're called the solubility rules, and this is just from many years of observation that they came up with these rules. Okay, so here's a little table that'll help you out with that. Compounds that are mostly soluble. Okay, well, let's start over here. We have our all of our compounds. If you have something that is with a lithium ion, a sodium ion, potassium, ammonium, nitrate, or acetate, they are always going to be soluble. Okay, now compounds that are mostly soluble. Let's look at this table. So compounds containing chlorine, bromine, and iodine. Okay, now you got to look at the next rule. Does the compound contain silver, mercury, or lead? Okay, if it does not contain silver, mercury, or lead, and you have a chlorine, a bromine, or an iodine, it's going to be soluble. If it does contain a silver, a mercury, or a lead, it's going to be insoluble. All right, sulfate. Okay, this is one that we see a lot. Okay, does the compound also contain calcium, strontium, barium, or lead too? Okay, if it does not, then it's going to be soluble. If it does, then it's going to be insoluble. All right, so if something is soluble, you guys are going to write AQ. Okay, if it's insoluble, you guys are going to write solid. So let's look at an example. The solubility rules indicate that compounds containing lithium are soluble. Okay, so compounds like lithium bromide, lithium hydroxide, and lithium carbonate dissolve in water, and they would dissociate completely into ions, and you would have a strong electrolyte solution. So these guys here in solution, it would be just ions, Li pluses and Br minuses, okay, or Li pluses and OH minuses in solution. So electricity would flow through readily. The solubility rules state that compounds containing nitrate are also soluble. Okay, so compounds like AgNO3, PbNO3, CaNO3. Let's figure out the names of these. Silver nitrate. This is, let's see, this is lead 1 nitrate. Okay, and this is calcium nitrate. They dissolve in water and they also form strong electrolyte solutions, okay? Because the solubility rules say that they're soluble. So in solution, you would just have a bunch of pluses and minuses flowing throughout the solution, making that current easily able to go through there. All right, let's look at hydroxide. Okay, so hydroxide, you have to look and see if hydroxide is with a lithium, a sodium, a potassium, or an ammonium. If it is with one of those, it is going to be soluble. So in that case, you would write aqueous as the phase, okay? If no, then you're going to look, does the compound also contain calcium, strontium, or barium? Okay. If no, then it's insoluble. Okay. And you would write solid. Okay. And if it is, then it's slightly soluble. All right, then we have compounds containing sulfide. So you have to look first to see if they're with any of these. If yes, they're soluble. If no, they're insoluble. And then we have carbonate and phosphate. Are they with the lithium, sodium, potassium, or ammonium? Yes, soluble. No, insoluble. So table 7.2 in your book sums up these rules for you. Take a look. So in precipitation reactions, these are reactions in aqueous solutions that form a solid. Okay, so sodium carbonate in laundry detergent reacts with dissolved magnesium and calcium ions to form solids that precipitate from solution. These reactions are examples of precipitation reactions. Reactions that form a solid, and the solid is called a precipitate. That is a precipitation reaction. All right, so here's an example of a precipitation reaction. You have potassium iodide, that is an aqueous solution, and you have lead to nitrate, which is an aqueous solution. And you'll see when you combine them together, you get lead to iodide, which is a solid, and potassium nitrate. Okay, so lead to iodide. Let's go back and look at our solubility rules. All right. Okay, here we go. We have our iodide, and it says when any of these are paired with silver, mercury, or lead 2, they are insoluble. Okay, so we go back to this reaction. Insoluble means that they are solid, and that means that a precipitate is formed. A precipitate can be like a chunk, or it can be something cloudy, but it's something that is kind of solid there in the solution. All right, here is a another reaction. Okay, this is a reaction of two aqueous solutions, Ki and NaCl. Okay, this has no reaction, and this is because when you have, if you remember, the cation of this guy, oops, here we go. The cation of this guy would go with the anion of this guy, and if you remember from the solubility rules, something that is with a potassium is going to be soluble, and then the cation of this one is going to go with the anion of this one, and if you were to look at the solubility rules, that's also going to be soluble. So both of your products here would be aqueous. Aqueous, okay. So you wouldn't have any precipitate floating in the solution or a chunk hanging out down here on the bottom, okay? So this would be considered no reaction. All right, we'll pick this up in a little bit.